Hello, and welcome to Little More Learning. Today, we will be starting with applied physics. We are going to be covering about interference of light and related topics in this video. What is interference? Interference is the phenomenon in which two waves superpose to form the resultant wave of the lower, higher, or same amplitude. Now comes coherent and incoherent sources of light. Coherent sources are light sources that emit waves with a constant phase relationship and the same frequency. These are essential for producing clear and stable interference patterns. Example for coherent source of light is laser light. Incoherent sources of light. Incoherent sources emit light waves that have random phase differences, meaning their waves are not in sync and vary over time. Example can be an ordinary light bulb. Time to study types of interference. There are two main types of interference: constructive interference and destructive interference. Constructive interference. When two light waves meet in such a way that the crests, high points, of one wave align with the crests of the other, their amplitudes, strength, add up. Think of it like two friends lifting something together working in sync, they can lift more. Destructive interference. When the crest of one wave meets the trough, low point, of another, the waves cancel each other out, reducing or even eliminating the light at that point. It's like two forces pulling in opposite directions, canceling each other out, resulting in darkness or reduced light intensity. You can better understand constructive and destructive interference through this diagram. Interference due to division of wave front. This type of interference occurs when a single light wavefront is split into two or more parts that travel different paths and then meet again. The two commonly known experiments that demonstrate this type are Young's double-slit experiment and Fring L Biprism experiment. Interference due to division of amplitude. In this method, instead of dividing the wave front, the light's intensity, amplitude, is divided. It involves splitting a light beam into two or more beams of lesser intensity. These beams take different paths and are recombined later to produce interference. This type is commonly seen in more modern and practical setups such as Michelson interferometer and Newton's rings. One of the most famous demonstrations of light interference is Thomas Young's double-slit experiment, first conducted in 1801. It beautifully illustrates how light behaves like a wave, creating a clear and visible interference pattern. Experiment setup. In this experiment, light from a single coherent source, like sunlight or a laser, passes through two very narrow slits, placed close together. The light emerging from these slits acts as if it comes from two new coherent sources, with each slit producing light waves that spread out in all directions. What we observe is superposition of waves, that is, when the light waves from the two slits overlap, they superimpose, which means they combine. Constructive and destructive interference, that are bright and dark bands on the screen. These bands are evenly spaced and are known as an interference pattern. The bright bands are where constructive interference happens, and the dark bands are where destructive interference occurs. In this diagram, you can understand how double slits produce two coherent sources of waves that interfere. Light spreads out, diffracts from each slit because the slits are narrow. These waves overlap and interfere constructively, bright lines, and destructively, dark regions. We can only see this if the light falls onto a screen and is scattered into our eyes. Significance of this experiment includes that it provided compelling evidence for the wave nature of light. Before this, the dominant belief was that light behaved purely as a particle. Apart from this, the distance between the bright fringes in the interference pattern can be used to calculate the wavelength of the light used in the experiment. The position of the bright and dark fringes depends on wavelength of light, distance between the slits, distance from the slits to the screen, and angle of interference. For constructive interference, d sine theta equals m lambda. For destructive interference, d sine theta equals m plus half whole multiplied by lambda, where m is the order of the fringe. Principle of superposition of waves. According to this principle, when multiple waves meet, the resulting wave is simply the sum of the individual wave displacements at each point. Key points. Wave interference. When two or more waves pass through the same point, they interfere with each other. This interference can be constructive or destructive, depending on the phase of the waves. Mathematical representation. If two waves have displacements y1 and y2, the resultant displacement y is given by addition of the waves. This addition of displacements applies whether the waves are in phase, constructive interference, or out of phase, destructive interference. Applications of superposition principle. The principle of superposition explains the appearance of interference patterns in phenomena, such as Young's double-slit experiment. In acoustics, the superposition of sound waves can result in phenomena such as beats, where the interference of waves of slightly different frequencies leads to variations in sound intensity. In the case of standing waves, the superposition of waves traveling in opposite directions creates fixed points called nodes and antinodes. The Fring L Biprism experiment is an elegant demonstration of light wave interference using a prism setup. The biprism splits a single light source into two virtual coherent sources, allowing us to observe the interference of light without the need for two separate sources, as in Young's experiment. A biprism consists of two prisms joined base to base, with a very small refracting angle, usually around 1 degree. When light from a single narrow source passes through the biprism, the prism's refracting surfaces bend the light, causing it to appear as if it comes from two closely spaced virtual sources. Experiment setup includes a monochromatic light source, a biprism placed in the path of the light coming from the slit, and interference on a screen. Working principle. The biprism bends the light from the single slit, creating two virtual coherent sources. These sources produce overlapping light waves that interfere with each other, leading to the characteristic fringe pattern. The interference fringes are observed as bright and dark bands due to constructive and destructive interference between the two sets of waves. Mathematical analysis. The distance between the fringes, fringe width, is given by the formula fringe width beta equals lambda capital D divided by small d, where lambda is the wavelength of the light used. D is the distance between the biprism and the screen, and D is the separation between the two virtual sources created by the biprism. This is the diagram for Fring L Biprism. When a monochromatic light source is kept in front of biprism, two coherent virtual sources S1 and S2 are produced. Fringes are of equal width. The convex lens is mounted between the biprism and eyepiece. There will be two positions of the lens when the sharp images of coherent sources will be observed in the eyepiece. Significance of the biprism experiment. The Fring L Biprism experiment confirms the wave nature of light and helps to measure the wavelength of light. It's also useful in situations where it is difficult to physically have two coherent sources, as in Young's double-slit experiment. Here, a single light source is enough, and the biprism creates the effect of two sources. Let's understand interference from parallel thin films. When light interacts with thin films, like soap bubbles or oil slicks, fascinating color patterns often appear due to interference. This phenomenon is known as thin film interference and occurs when light reflects off the surfaces of a thin, transparent film. How it works. When light hits a thin film, part of the light reflects off the top surface, and part of it travels through the film and reflects off the bottom surface. The two reflected waves travel different paths, and as they overlap, they interfere with each other. The thickness of the film and the wavelength of the light affect the type of interference observed, which is why we see colorful patterns in thin films, especially under white light. Mathematical condition. The condition for constructive interference is given by 2nt equals m plus half whole multiplied by lambda. And for destructive interference, 2nt equals m lambda, where T is the thickness of the film, N is the refractive index of the film, lambda is the wavelength of the light, m is an integer representing the order of interference. This phenomenon finds its applications in anti-reflective coatings and soap bubbles and oil films. As we can see in the diagram, light is undergoing reflection at two different surfaces with two different refractive indices. Hence, these kinds of reflection are termed soft reflection and hard reflection. Soft reflection, when light is reflected off from the surface within the lower medium of the lower refractive index. As a result, no phase shift can be observed. Hard reflection, when light is reflected off from the surface within the medium of a higher refractive index. As a result, a phase shift is observed. A wedge-shaped film is a thin film whose thickness varies linearly from one end to the other, resembling a wedge. When light reflects off a wedge-shaped film, interference occurs similarly to parallel thin films, but because the thickness of the film changes gradually, the interference pattern appears as alternating light and dark fringes along the wedge. How it works. Light reflects off both surfaces of the wedge-shaped film, top and bottom. Due to the gradually increasing thickness of the film, the path difference between the two reflected waves varies continuously across the film, leading to a series of interference fringes. Mathematical condition. For constructive interference, 2nt equals m lambda. For destructive interference, 2nt equals m plus half whole multiplied by lambda, where T is the varying thickness of the film, N is the refractive index, lambda is the wavelength of the light, m is the order of the fringe. Application of wedge-shaped films are in measuring small distances. The wedge-shaped film is bound by two plane surfaces inclined at angle alpha. The thickness T of the film varies uniformly from 0 at the edge to the maximum value at the other end. A ray of light AB incident on the film will be partially reflected along B and partially transmitted along BC. The ray BC will be partially reflected along CD, which will be again partially transmitted along BF. The two rays B and BF in reflected light diverge. Newton's rings is a famous interference pattern created by the interaction of light waves reflected from a curved surface and a flat surface. When a convex lens is placed on a flat glass surface, a pattern of concentric rings, alternating bright and dark, forms. These are called Newton's rings. How it works. When light passes through a thin air film between the curved surface of a lens and the flat glass, it reflects off both surfaces. These two reflected waves interfere, creating the concentric circular fringes known as Newton's rings. Mathematical analysis. For dark rings, destructive interference. Rm equals under root m lambda r, where Rm is the radius of the m dark ring, r is the radius of curvature of the lens, lambda is the wavelength of light, m is the order of the ring. Application of Newton's rings include measurement of lens curvature and inequality testing. When a parallel beam of monochromatic light is incident normally on a combination of a plano-convex lens L and a glass plate G, as shown in figure, a part of each incident ray is reflected from the lower surface of the lens, and a part, after refraction through the air film between the lens and the plate, is reflected from the plate surface. These two reflected rays are coherent. Hence, they will interfere and produce a system of alternate dark and bright rings with the point of contact between the lens and the plate as the center. These rings are known as Newton's rings. The Michelson interferometer is an optical instrument used to measure very small distances, detect changes in refractive index, or even observe tiny wavelength variations. It uses the principle of interference by splitting light into two paths and then recombining it to produce an interference pattern. It works with beam splitter and recombination of beams. Mathematical condition. The interference pattern can be used to measure small distances delta d by counting the number of fringes m that pass a point when the mirror moves. The relation is given by delta d equals m lambda by 2, where m is the number of fringes, lambda is the wavelength of light. Michelson interferometer applications include precision measurement and detecting small changes. Figure depicts the interferometer and the path of a light beam from a single point on the extended source S, which is a ground glass plate that diffuses the light from a monochromatic lamp of wavelength lambda naught. The beam strikes the half-silvered mirror M, where half of it is reflected to the side and half passes through the mirror. The reflected light travels to the movable plane mirror M1, where it is reflected back through M to the observer. The transmitted half of the original beam is reflected back by the stationary mirror M2, and then toward the observer by M. That's a wrap for today. Stay tuned for the other parts of applied physics. If you liked the video, then please like, subscribe, and comment.